My name is Christopher Kelson, and I'm Senior Geologist here at Atlantic Testing Laboratories. Here at ATL, I work with everything that involves geology, rocks, and minerals, but also do petrographic analysis of said items, as well as concrete and airborne analysis of concrete and so on and so forth. So today what I'd like to do is take about an hour or so and dig into the geological side of some of the hazards presented to engineers. And as noted here on the title slide, this is part one. There is a part two, and we'll talk about that in a little bit. In fact, that's 2 weeks from today, but we'll talk more at the end. So this is a big topic, and we could easily spend weeks and weeks and months talking about all of the different types of geologic hazards. So this is definitely a very topical synopsis of some of the major ones and most common types. So as Lindsay mentioned, there will be some really difficult questions popping up here and there throughout the presentation. So when they do, please submit your answers to them to Lindsay, and we'll keep going. And then at the end of the day, we'll talk to you about getting your PDH credit for this. Also, feel free to submit any comments or questions, as she mentioned as well, and at the end we'll address them. Okay, so just a brief explanation of what a geologic hazard is. Well, it could be pretty much anything related to geology. Could be earth materials, which is anything from soil to rocks to minerals, water. Geologic events, right? Earthquakes, volcanic eruptions, landslides, things we're all obviously familiar with, or at least heard about, and geologic processes, the weathering and erosion of rocks and minerals, formation of karst. We'll talk about that a little bit later on. So pretty much anything can be classified as as a potential geologic hazard if it's potentially hazardous to life and or property. So the key to this webinar is basically to put out the idea that identifying these potential geologic hazards and preparing for them is a lot better than reacting to them after they've already happened and trying to repair the damage that's done by not being prepared for them. So in this presentation, we're going to cover five separate topics. The first two are related to each other. We're talking soils in different capacities. We'll talk about seismic activity, earthquakes, basically, right, and in particular faults and liquefaction, and then talk about karst, formation of karst, and then rocks in general. So a shrink swell soil is one that volumetrically decreases or increases for whatever reason, and there are a number of mechanisms that can make this happen. Water loss and absorption is a big one. Constituent minerals within the soil, sulfides, for example, pyrite, right, fool's gold, for example, oxidizing in the soil and expanding because of that, or the oxidation of that sulfide mineral might generate the formation of a secondary mineral, which takes up more space than the precursor, right? And this would expand. Changes in temperature, etc. So please just keep in mind that that soils and rocks, for that matter, can shrink and swell, especially from these same mechanisms. At the end of the day, the end result is the same: soil settling, heaving, potential foundation damage. So that's why these are potential geologic hazards. And by the way, for the lack of a laser pointer that I can use with everybody, please follow the mouse cursor there on my screen. So soils that decrease or increase volumetrically due to water loss or absorption contain certain clay minerals that allow that to happen. And one soil that you might be familiar with, at least topically hearing the name, is bentonite or bentonitic soil, right? Montmorillonite is the major mineral ingredient in that type of soil, and that's the subgroup of minerals that are responsible for the increase and decrease in volume. So Montmorillonite belongs to the smectite group of minerals, and it's a phyllosilicate. So it's a silicate because it contains the silicon and oxygen. It's a phyllosilicate because of its phylo meaning sheet, right? So its sheet-like structure puts it into the phyllosilicate group, mineral group. There's a formula if you'd like to see that. And if you were to look at Montmorillonite, for example, on an atomic level, on a molecular level, you'd see that it's what we call a 2-to-1 structured clay. There are two what we call tetrahedral sheets that are sandwiching an octahedral sheet in between them. And you can see the elemental constituents of each of these sheets down here in the lower right. Well, when you have many of these TOT sheets sandwiched together, you have a space in between them in which water and other cations can get in there and hang out. So this is where the water goes. In the case of Montmorillonite, this is how Montmorillonite can absorb water in that interstitial space between the TOT layers. So what happens is the more water you introduce and the more Montmorillonite you have in the soil, the soil can expand anywhere from 22 to almost 50% based on those two factors. The swelling pressure, the pressure that would be acting against any sort of foundation or building that's built on or against this material, can range anywhere from little over one atmosphere to about six and a half times atmospheric pressure. So it's nothing to laugh off. I mean, this could be a potentially bad thing. Here are some pictures of what shrink swell soils do to real structures. So we're looking at the foundation of a house. There's concrete, brick on top of it, and then obviously the grass is growing on soil that is expanding, it's shrinking and swelling, and the expansion is pushing the foundation, and you can see that. Inside that same building, it's easy to see if you look at the center of the screen. You can see there's a plumb bob there showing straight up and down, and how the walls have been pushed in because of it. So the idea here is, to try to basically understand if shrink swell soils are a potential hazard, a potential issue of where you live or where you work or where you're building something. So there are a couple ways around this. First of all, maps exist of the entire United States. Here's one that we're looking at now that basically show where the potential for shrink swells, expansive soils, right, where they might occur nationwide. And again, remember, there are many mechanisms that can make soils increase or decrease in volume, right? So this is just a very, very generalized idea, but you can see in some places of the country it's not really an issue. In other places it's more so. Certain maps exist on a statewide level. Here's Texas for an example, where they actually have a map delineating the different counties too, and color coding where the frequency of expansive soil is anywhere from high to low or very limited. They're not telling you what the mechanism is for the soil to expand, but they're just saying wherever it's red, the frequency is higher. And something we can do that's a little more site specific would be to actually sample the soil and analyze it, and that's what I do quite a bit here for clients, either soil or rock, right? We're looking to try to identify if expansion is possible. So one way to do this is through the use of X-ray diffraction, or XRD, and XRD is a microanalytical technique and instrument that essentially identifies the mineralogical constituent of either a rock or soil. It doesn't tell you what those minerals are made of. It doesn't tell you elemental constituents. It just tells you who's home. And in each mineral, because of its internal crystallography will produce basically a unique fingerprint that the XRD can see. So in this example I'm showing on the screen here, this particular sample was comprised of four things. There was so each mineral that's present in the sample gives a unique what's called a peak pattern. It's the fingerprint. So wherever you see a Q, those are peaks because of the presence of quartz. F, feldspar, right? And there's M, which is Montmorillonite. So in this sample, we would be able to identify that Montmorillonite is present. Scale on the y-axis is basically just it's counts per second. It's comparable to a quantification of the material in there, but it just gives you an idea that the taller the peaks, the more that stuff is in there. Okay, question number 1.
Back to you, Chris.
Okay, thanks. And question number 1, which of the following is not a process that can cause soil to shrink or swell? Number C is not one of the options, dispersion of carbon. Let's switch gears slightly and talk about soils that are toxic or potentially toxic, and these are soils that either contain something or produce something that could be dangerous to our health. And obviously the soil itself is a function of the rock from which it's derived, right? So if the surrounding rocks contain minerals that contain something that's potentially toxic, well, the soil obviously will have that same thing in it. In this case, we're going to be talking about uranium and radon. Okay, so first of all, uranium is a relatively common element. It occurs in all rock types, but especially metamorphic and igneous rocks. Zircon and uraninite are a couple fairly common uranium-bearing minerals. As you well know, uranium is radioactive, and over time it will decay through several steps, ultimately to lead. And it does that over the course of billions of years. Well, one of the daughter products within this decay sequence or decay chain is radon, and radon is a carcinogenic gas that's produced by the natural decay of uranium. Now radon's not a problem if you're outside and it's outside and it's no big deal, but if the radon is trapped in an enclosed space or a poorly ventilated space, like a basement of a house or a structure, right, or building, then it could be an issue. So in this picture, we have our bedrock, which contains the uranium-bearing minerals. The soil derived from the erosion and weathering of that bedrock, weathering and erosion of that bedrock also contains the uranium. If the uranium in the soil and bedrock is decaying, it's producing radon all the time. And if the foundation to the structure is cracked, for example, the radon gas can easily seep into the structure and into the basement. So one way to fight this would be to make sure, obviously, that the foundation is sealed up, and even include a pathway little fan-driven pathway for whatever radon that might get into the beneath the foundation to be extracted and vented out to the atmosphere. Again, this is a pretty serious issue, so serious enough, in fact, that these radon test kits can be had at your local home improvement store. And I found this one on the shelf. I'm not advertising for it. I'm just saying I found it. On the back, they give you some statistics from 2011. So these are about 10 years old, but the numbers are pretty comparable to present day, where radon gas causes cancer, and it's second only to smoking in lung cancer, causing lung cancer. And when you compare deaths due to cancer from radon gas, it actually outstrips deaths from drunk driving and falling out at home and drownings and fires. So it's a big deal. Question number 2.
Chris, you can continue.
Thanks, Lindsay. Question number 2. The radioactive decay of what element produces radon? And that is D, uranium. Let's switch gears completely and talk about some geologic hazards that are associated with seismic activity. And whenever you see the word seismic, of course, we think about earthquakes. These are geologic events or processes that are powered by the energy released, basically an earthquake, due to movement of the Earth's tectonic plates. So a lot of geologic hazards are associated with the movement of Earth's tectonic plates. Surface rupture, right? Faults, tsunamis, ground shaking, which then produces things such as landslides and seiches and liquefaction. So we'll talk about some of these in turn. Basically, this is probably a time warp back to your high school or science class, where I'm going to give you a brief geology lesson in 10 seconds or less here on plate tectonics. So there's the Earth's crust, right? The Earth's outer layer is the crust, and underneath, and that's part of the lithosphere, and that's the outer 100 kilometers of the planet Earth, and it's completely solid. And think of the Earth's lithosphere, including the crust, as like an eggshell, like a broken eggshell, and each piece of the of that broken eggshell is moving around relative to the other pieces. So each one of those pieces we're going to call a plate, and each one of those plates has a name. And in this map, each one of those plates is color coded, so you can kind of tell them apart. And also on this map, you can see these red arrows, which are showing relative movements of adjacent plates. So there are three types of ways that a plate can interact with its neighbor. A plate can diverge from its neighbor, right? They separate. That's called a divergent boundary. Two plates can converge. They can be basically slamming into each other head on. That's a convergent boundary. And a transform boundary, such as right here, San Andreas Fault, right? Great example of this in real life. This is where the two plates are basically sliding past each other. So depending on the type of stress is involved here, whether it's a tensional stress pulling plates apart, compressional stress ramming them together head on, or a shear stress, right, making them slide past one another, you get not different earthquakes, but you see different geological features associated with that. Let's focus just on the United States, the contiguous United States, and again, the name of the game here is to have an idea of where you are in the world, and is your location going to be potentially affected by seismic activity. So with this map of the United States, wherever you see an area that's red, that's an area that's going to be prone to earthquakes, and probably big ones, more of them anyway. And then white is essentially nothing. What's interesting here is that throughout the United States, you definitely get areas like the entire West Coast prone to a lot of seismic activity, and even areas in the East and in the Midwest that are associated with earthquakes as well. We'll talk about that in a second. As we mentioned before, rocks break due to stress, and when the rocks just can't take the stress anymore and they break, that release of energy is what's called the earthquake. The Earth's surface, in response to the rocks breaking, can be fractured, right? And along that fracture, movement can occur. That's then the fault, and the rocks can either be vertically displaced across the fault from one another, or laterally displaced, or both. Depends on the type of stresses involved. And when we say displacement, we anywhere from a few millimeters to kilometers worth of displacement. So one of the obvious geologic hazards of earthquakes or seismic activity is the rupture of the Earth's surface. So obviously this isn't very conducive to roads or buildings. This isn't good. So this is a potential hazard. Surface displacement. Again, you've got two packages of rocks that are sliding past one another due to the movement, due to the release of energy and the subsequent movement. This is a satellite image of a large fault in China, and the rock layers are color coded. You can see that when these rocks were formed, all the red layers were attached to each other, all the blue layers were attached to each other. And now they're separated into two separate packages by this fault. So this type of fault is what we call a lateral fault. In particular, this is a left lateral fault, and this is a result of tensional stress acting on this part of the Earth's surface. This is an example of surface displacement caused by tensional stress. So in this part of the world, which this is Nevada, actually, the crust is being pulled apart under tensional stresses, and where two blocks of rock are basically separating from each other, you get this is the fault, and this is what we call a normal fault, and that surface is actually called the fault scarp. If you take a closer look at the fault scarp itself, you can actually see where one block of rock moved against the other one. This is the actual fault itself. A fault is a planar feature, right? It's a 3D planar feature. It's not just a line. So this is the surface of the fault itself, and where you had this block sliding down against this block, producing something we call slick insides. So if you see this out in the field, you're looking at a fault. So how to mitigate seismic activity? It's kind of a trick question because you can't stop it, you can't predict it, right? No one can predict earthquakes. We know where they're going to happen, and in general time frames, kind of when they're going to happen, but you can't predict them. So preparation is the big deal here. Identify your potential for seismic activity. First of all, understand where you are relative to one of these plate tectonic boundaries, and in particular relative to a fault. So I'm going to use a map of New York State, a very generalized map of New York State. Remember that New York State obviously is on the eastern half of the continental United States. It's nowhere near an active plate boundary, but we still see faults or fault systems in New York State, and we still get earthquakes in New York State. This one in red is called the Clarendon-Linden fault zone, and it's typically the location of more faults, more earthquakes there than anywhere else in the state. So it's just kind of highlighted there. But everywhere you see one of these yellow lines, I mean, that's a fault. So that's a fault that was either, that's a fault that was either alive, a billion years ago, or, it was active last Tuesday, but whatever the case, it's a fault. Now, it being there means that it's, there's still a physical weak point in the Earth's crust where that fault is, and even ancient faults can be reactivated from time to time. Understand that the continental crust is billions of years old, and it's ancient, and it's being tweaked on one end or the other, or both, from plate tectonics and plates moving against it and whatnot. So once in a while you get a release of energy in places that aren't associated or near a plate boundary, and this is an example of one of them. In fact, if you look at earthquake hazards again at New York State, red is bad, or I guess red is more hazardous than green areas. You can see that Clarendon Linden Fault zone here, but also the St. Lawrence River Valley is also a zone prone for earthquakes, and it's a fault as well up there. So again, no way to really stop this or predict it, but you just be prepared for it. As far as another thing, obviously, you can do is when you're building buildings, keep seismic threats in mind, and so adhere to building codes for new construction. Make sure you're doing everything you can to make sure that the new structures can do their best to ride out any seismic activity, and for old construction, possibly retrofit it with motion resistant measures. Let's switch gears slightly. We're still talking about seismic activity, but in this case, we'll talk about liquefaction. We've all heard this term before. Let's discuss it a little bit more in detail. Liquefaction is a phenomenon that occurs in water-saturated, unconsolidated soil. So loose soil that's full of water is a prime liquefaction candidate, prime candidate for liquefaction to occur. As long as there aren't any, as long as that soil isn't being disturbed, even though it's saturated with water, it can still hold weight. But as soon as that soil is jiggled, for lack of a better word, then the particle-to-particle cohesion is lost, right? All the water is essentially a lubricant, and as well as long as the soil has some energy moving through it, it momentarily behaves as a liquid, not as a solid. And as soon as the energy move through it stops, then it goes back to behaving more like a solid. Just right. A lot of my students ask about this, and yeah, the soil does not actually turn to liquid; it just behaves like it. So we see evidence of this. We see evidence of this worldwide. Here's an example in 2011, the big Christchurch, New Zealand earthquake. This is a car that was driving on this very water-saturated soil. The earthquake energy came through the area. The soil lost cohesion, acted as liquid. The car sank into it, started to sink into it, and then when the earthquake stopped, we're back to solid state. The soil acting as a solid state. A manhole cover and pipe here in the foreground and also in the background here in Japan in 2011. I mean, again, liquefaction caused these things to essentially rise out of the ground. They're basically more buoyant than the surrounding soil, and when the seismic energy pulls through the area, these things rose to the surface, kind of like boats floating on the water. Another example from 1964, entire blocks of buildings, rows of buildings just fall over because the soil lost its cohesiveness. Liquefaction occurred here, and things just toppled over. So how to mitigate this? Again, identify the potential for it. How close are you to a tectonic plate boundary? Are you, are you on top of unconsolidated soil? Are you sitting on bedrock? Right, bedrock's better, right? Unconsolidated soil is potentially the problem. How deep is the water table where you are? And also, what do you know about the soil itself? It seems that that fine sand particles tend to exhibit the effects of liquefaction most compared to the other particle sizes. Just to give you a quick real-world example of liquefaction. So this is a cross section, an east-west cross section through part of the Salt Lake Valley in Utah. Salt Lake City would be about right up here where my cursor is. Sorry, about right there. So the Salt Lake Valley is bordered on the east and west by mountain ranges, and the mountain ranges are separated from the valley by faults. So the valley is essentially full of soil derived from the erosion of the mountains on either side to the east or west of it. So in the cross section, you can see the faults in red and how they propagate down with depth. In the middle of the Salt Lake Valley, you can see there is semi-consolidated sediment. I mean, loose sediment down to almost 3,000 feet in the center of the valley, which means if you were to make a geologic hazard map, where liquefaction potential would be the worst during an earthquake. This is the map that the Utah Geological Survey came up with. Again, the mountains are here, but notice that the center of the valley where the loose unconsolidated sediment is the thickest, that area is going to be hit hardest by an earthquake, even though the earthquakes would be generated probably up by the mountains, which wouldn't show much liquefaction. You'd have surface rupture and things happening there, but liquefaction is worse in the center of the valley. So how do you mitigate this? Just kind of be prepared for it and understand it's a possibility. Ability, I think, is probably your best bet. It's possible to treat or prepare the soil. You can compact it, make some soil or grout, cement with it or grout it or whatnot to try to reduce its susceptibility to liquefaction. But yeah, it's kind of site specific is what you might be able to do with it. All right, question 3, please.
Chris, you can continue.
Thanks, Lindsay. Okay, question 3. Liquefaction is most pronounced in areas underlain by loose, unconsolidated soil. Switching gears one more time to a different form of geologic hazards. This is karst, and I'm sure you've all heard of the name. We're going to define it here. Karst is actually a type of topography, and it develops when certain rock types are actually dissolved in water. So water is the key here. Water is the key, and the type of rock is key, and you have to have both of those things present, or this doesn't work. Okay, so first of all, what are the soluble rock types? Just list them: limestone and marble. I mean, those are 2 separate rock types, but they're made out of the same thing: calcium carbonate, dolomite, rock salt, and gypsum. These are the 5 rock types that are susceptible to having karst features form in them. Now again, you need to have water there as well, liquid water. So if you have limestone, there, but you don't have any liquid, so if it's the middle of the Sahara Desert, then you have limestone, karst isn't going to be happening. Or forming. If you have limestone in Antarctica, not so much, right? You need to have liquid water in combination with these rock types. Now, limestone, marble, and dolomite are kind of special subgroup of these rocks. As you know, rocks, you can dissolve salt in water and gypsum as well, but these limestone, dolomite, and marble dissolve in water due to the presence of carbonic acid in the water. So carbonic acid is a naturally occurring thing. Water plus CO2, both of these things are in the atmosphere or in the ground, right? When those two combine, you produce carbonic acid, and it's the carbonic acid that actually dissolves away the limestone or marble or the dolomite. On areas of the Earth's surface where there's a lot of CO2, say in industrial areas or urbanized areas, right, where you have a high population of people, for example, a lot of cars, right, power plants, whatever, you're producing CO2 because of just the population. The amount of carbonic acid in the rainwater will be higher than if those factors weren't there. The presence of carbonic acid in rainwater is by and large what's responsible for giving rainwater its slightly acidic pH. So rainwater, 5.5 or so pH is not a 7, but the more CO2 you have, the more carbonic acid, the more acidic the rainwater will be. So karst features, you've heard of these, you've probably seen pictures of them. The news programs love to talk about these things because they're spectacular when they happen. We're talking about sinkholes, caves, disappearing streams, underground rivers. These are all karst features of karst topography, and there's a block diagram giving you an idea of what these are. So a sinkhole. Here's a picture of one, somebody's house falling into it. A sinkhole is a karst feature, and basically the soluble rock that's under the surface here was dissolved away enough that it couldn't support the house above it, and the whole thing just slumps into the hole. That's the sinkhole. How do you mitigate karst? Well, again, being prepared for it and identifying the area in which you are, and if these rock types are there where you are, is the first step. So consult geologic maps, hire a geologist to do some reconnaissance or some field work, some mapping of the area to see if these karst susceptible rocks are there in the first place. Now you can consult general maps. I mean, here's one of the entire contemporaneous United States showing where karst can potentially form. And this is helpful on some level, but again, nothing beats on-site inspections and having a trained eyeball go out and look at this stuff in person. Here's a map of New York State showing the distribution of limestone, for example. Limestone, obviously, very susceptible to karst forming. So maps exist showing where these rocks are on the Earth's surface. Now, karst can form underneath the surface. So even though limestone, for example, might not be exposed at the surface and you can't see it while you're standing out there, under the Earth's surface, if it's there, it's still susceptible to dissolution and the formation of these karst features. A lot of this depends again on the climate. So the more humid the climate, the higher potential this is going to form. Also, it depends on the depth of the water table. If the water table is closer to the surface versus further down, right, that will dictate how much water and rainwater, right, charged with carbonic acid in particular, can interact with the subsurface. But basically, once karst starts to form, once the caves start to form, once the sinkhole starts to form, once this is starting, it's just a train that's not going to stop. And so it's just identifying the danger, I think, is the biggest step in the process here. Okay, quiz 4. Question 4.
Chris, you can continue.
Thanks, Lindsay. Question 4, which acid is formed from water and carbon dioxide that creates karst topography in limestone, marble, and dolomite? And the answer is C, carbonic acid. Let's wrap up this conversation by just talking about rocks in general as being geologic hazards. First, understand that they can be hazards based on either their mineralogical composition, right? So if these rocks contain, as the example we used before, uranium, for example, right? Then you have to, think about the potential hazard they pose with respect to, radon being produced, or radioactivity if there's enough uranium in the rock. But also understand that their physical characteristics not only is due to their composition, mineral composition, but also how they were formed. So the 3 types of rocks, right? Sedimentary rocks, igneous rocks, and metamorphic rocks, all form under different geologic circumstances and under different conditions, and how each forms can provide each of those rock types with a potential kind of unique hazard all to itself based on the differences on these 3 types. So just walking through a few ideas here. Let's talk about sedimentary rocks as geologic hazards. So sedimentary rocks, these are rocks that are either made by pieces or fragments of other rocks that have been weathered from some parent outcrop, and then the particles deposited someplace and then cemented together. So these are your siltstones and your sandstones and your shales, right? Sedimentary rocks could also be things like limestone or coal. So these are or rock salt. So these are rocks that are either formed through chemical means or through biologic activity, or both. This picture is showing a typical feature of sedimentary rocks, something we call bedding planes and interbeds. So a bedding plane is basically just the small separation that exists between when one layer of sediment was deposited before the next layer was put down. Okay, so that little gap, or that little separation between one layer of sediment and another, is called a bedding plane. An interbed is when you have a different sedimentary rock type within another sedimentary rock type. So for example, you can have well, in this picture we're seeing here, we have a sandstone. We have a sandstone, okay, but in between the deposition of sand layers, Mother Nature was depositing layers of silty mud, and then another layer of sand was put down, and then more silty mud, and then another layer of sand, and more silty mud. So you have these interbeds of silty mud in between the sandstone layers. What happens here is that we have preferential weathering of this rock. So the layers that are comprised of these silty mud are more susceptible to being weathered and eroded away than the layers comprised of quartz sand. So over time, you have this weathering profile that exists, where the layers that are more resistant to weathering stand out compared to the layers that are more susceptible to weathering. On a big scale, this could be a problem if enough of the softer material is worn away. Obviously, you can have huge portions of the more resistant ledges basically break off through lack of support and go downhill just due to gravity, right? So there's an obvious geologic hazard, but also it's possible that these rocks are tilted. In this case, they're horizontal, but in this case, they're tilted. Now this poses a different problem if we're tilting these sedimentary rocks that, again, layers of sandstone with say mudstone in between them. Well, that mudstone, by definition, is very rich in very fine silt and clay, and when you incline these layers of rock, those interbeds that are rich in clay and fine silt, especially in the presence of water, they get wet, might induce sliding, right, or slope failure, especially if the side of the hill, in this case, is parallel to the orientation of the dip of those beds. So this is what we call a dip slope, obviously, right? And the more you tilt these things off of horizontal, the higher a potential this hazard has to occur. Metamorphic rocks, the same thing. These are rocks that are formed from some pre-existing rock via heat and pressure. It's the pressure that creates what we call foliation. This is an outcrop of schist, and you can see these aren't, we want to call these layers, but this is actually foliation. So this was a big layer of clay-rich material, that, say, shale, that was subjected to heat and pressure. The foliation develops, but the same idea here, the foliation, the gap in between, one of these, what we call layers versus another one, could be the weak point where slippage could occur, especially if there's a dip slope involved and these rocks are tilted past horizontal up closer to the vertical. Here's an up close version of a view of what foliation is. This is again a schist, and what you see here and want to call layers that's the foliation. If you look at this close up, this foliation is actually produced by the elongation and parallel orientation of these phyllosilicate minerals such as micas and talc. And then just to round up some ideas about the whole dip slope failure, again, obviously, if we have some weight being put down on top of this hill and we have a dip slope here, again, the slope of the hill is parallel to the layers of shale or some other planes of physical weakness, where it be foliation as well. You can see the potential for failure to occur in a number of different instances. This is an interesting one down here in the lower left, where the problem is exacerbated by the addition of water, whether it's a leach field or just a lot of water getting in between these layers of rock from up where this house is. You're adding a lubricant, right, the water into this scenario, which would cause slope failure to probably occur even faster on a more regular basis, just because of the presence of water. And of course, one idea might be to drill into the hillside, put some drains in there to relieve some of that water pressure that would otherwise facilitate the slope failure. Question number 5, please.
Chris, you can continue.
Thanks, Lindsay. Question number 5, which of the following rock types possesses foliation? Foliation is a metamorphic rock thing.